Hi everyone, today we're going to be starting with Unit 6, and this is where we really jump into kind of the second major half of calculus. So everything in the first half focused around derivatives, and now we're going to be moving towards working with integrals. So this is going to give us an introduction into what that means. So you can see our targets at the top, and really today we're going to focus on doing some calculations, but really being able to interpret what those calculations are telling us. So we'll start off with a little review of where we've been and then move on to the big idea for this semester. So we spent the majority of last semester learning how to find the rate of change of a function. And we talked about two types of rate of change. The first was our average rate of change. Right, and so the average rate of change, well, let me go ahead and just sketch a picture. So I'm going to use my basic y equals x squared graph. So we said the average rate of change is the rate of change. I'm going to use this delta for change. So rate of change over an interval. So that was the important thing. It was over an interval, and I'm going to call that A to B. So graphically, what we could think of that is if I have A here, and let's make B here, right? I'm going to go find that point. I'll locate that point, and my average rate of change would be represented by this line. So it's the change over an interval, and we said graphically we represent that by the slope of the secant line, which we use to find that slope, just our regular old slope formula. So f of b minus f of a over b minus a. Now, when we moved on to instantaneous rate of change, I'm going to draw my same graph here. Oops. Now what we're talking about is the rate of change at a specific point. A point. So no longer an interval, it's a specific point, x equals a. So let's use my a here. Now I don't have that secant line, right? I'm talking about the rate of change at that one point. So now we're really talking about the slope of the tangent line. Which we know is the derivative. And we represent that by f prime of a. So those are the two types of change. So again, anytime we see instantaneous rate of change, we should be connecting that to the slope of the tangent that's connected to our derivative. Alright, so that's kind of where we've been, and we've done lots of applications using derivatives. So now for second semester, we're going to really be looking now at the area between the graph of a rate of change function and the x-axis. So for example, I'm just going to make up a function. Let's say I had a function that over an interval maybe did something like this. I'm just making it up. What we're talking about here is the area between the graph of the function and the x-axis. So everything that's trapped in between that function and the x-axis, that's the area we're talking about. So when we look at that area, it's actually telling us the accumulated change of that function over the given interval. So it's actually telling me how much change has taken place over that interval. And now I want to change this a little bit. Instead of saying we call this area, I'm going to say we represent this area, and I'll make a little caret here, using, so we represent that area using an integral. So a lot this semester is going to be now working with integrals. So here's what the notation is going to look like. first thing I want you to notice is this symbol here kind of looks like a long S. That's the symbol for integration. It's our integral symbol. And what it's really telling us, it's telling us to find the area between the curve and the x-axis. So the integral symbol is what tells us to find an area. Now the other thing I want you to know is this integral symbol and this dx, those always have to go together. Think of them like a parentheses in an expression. One starts the expression and one finishes it. So those always need to go together. Now, this is going to tell me this a, it's the left endpoint of my interval. It tells me I'm going to start finding the area at x equals a. B then is the right endpoint. And it's going to tell me to stop at x equals b. And then f of x is just my given function. Again, though, the big idea is when I see this integral symbol, for us it's really going to represent that area between the curve and the x-axis. So a second kind of big idea here is when areas are above the x-axis, so positive y values, they're considered positive. So let's look at this graph. I can see that between the curve and the x-axis, that area there is trapped, is above the x-axis, so that would be a positive area. Just like here, we have that area being trapped is above the x-axis, so that's a positive. When areas are below the x-axis, they're considered negative. So now this area here, trapped between this curve and the x-axis, that would be considered negative, as would this right here. Alright, so we're going to use kind of this basic information, what we know about integrals so far, to actually calculate some areas. So go ahead and flip. Alright. So at the top here it says the graph of f of x is shown, so I have a function f of x, and we want to use the graph to evaluate each of these integrals. So when I see this notation, what it's telling me is to find the area, and we won't write this out every time, but I want to make sure we're really clear on what that notation is asking for. We're going to find the area between the curve and the x-axis between my starting point is x equals -3 and my stopping point is x equals 0. So find the area between the curve and the x-axis between x equals -3 and x equals 0. So here's what I'm going to do. I have to keep in mind I'm looking for any areas that are above the x-axis, are going to be positive, below are going to be negative. So from 0 to 3, I can see here's my curve. It looks like from here to here, those are going to be above the x-axis, so those are going to be my positive areas. Now, from -3 to 0, I can see my curve drops below here, so now these areas that are trapped here are all going to be negative. So here's what I'm going to do. We're just using for right now to evaluate these integrals. What we can use right now are just our basic geometry formulas. So in other words, I know that this is a triangle. So I know that's going to be 1/2. The base of that rectangle, triangle is 1, and the height is also 1. So there's my positive area. Now this is negative, so now I'm going to have minus because it dropped below. Again, I have a triangle, so I have 1/2. The base of this triangle now is 2, and this height is going to be 2. So now I can simplify. It looks like I get 1/2 minus, let's see, this is going to be 2, which I know is just 4/2. So I get this as a -3/2, which I can kind of think intuitively. I know just looking at it, this is a much bigger negative area. So my ultimate answer should be negative because I had more negative area than positive. Let's check out number 2. So now I'm looking the integral from 0 to 4 of f of x dx. So from 0 to 4, my whole curve is underneath. So I'm going to trace out the curve. So I'm looking for the area between this curve and the x-axis from 0 to 4. So now this shape is a little weird, right? Between that curve and the x-axis are kind of these areas here. So we have to be a little creative in how I think about it. We can't directly find these areas using geometry, but hopefully what you see is that these areas are just my whole rectangle down here and subtracting out the semicircle. So what I'm going to have is I'm going to consider this whole rectangle. So the base is 1, 2, 3, 4. The height of that is 2. And then I'm going to subtract out this semicircle here, right? So I'm subtracting out this area because I want just what's left over. So I'm going to have minus pi, that's a radius of 2, and it's a semicircle. Now, the other thing I have to do is this whole quantity, I need to make sure is negative, and I'm sorry, that's kind of messy here. Since it's below the x-axis, I need to make sure I have a negative answer. So let's go ahead and simplify this. I've got negative, 4 times 2 is going to be 8. This is minus, let's see, 4 over 2 minus 2 pi. So my answer is going to be -8 plus 2 pi. And again, if we evaluate that, we would get a negative number, which we know is true because our area is below the x-axis. So now we want the area between -3 all the way over to 4. So now we could calculate these pieces individually, but hopefully intuitively, we should be able to recognize the area between -3 to 4 should just be the area that we found from -3 to 0. Plus the area we found between 0 to 4. I'm going to use my previous results to get that. So now I have my -3/2 plus, I had a -8 plus 2 pi, and I can simplify that. So -3/2 minus 8, let's see, plus 2 pi. Well, this would be 8 is 16 over 2, so -3 minus 16 is -19 over 2 plus 2 pi. So the big idea here is really to calculate integrals, we're just going to use our geometry formulas. Later we'll need other methods, but for right now, geometry will help get us through these types of problems. So now we'll just do a couple of these. I'm not going to do all of them, but let's look through a couple. It says to sketch a graph of the following functions to help you evaluate the integrals. Because again, right now we're really reliant on being able to use our geometry formulas. So sketching the graph should help us see how we can do that. So the first one here, maybe make a note to yourself. Hopefully this formula, so it's going to look something like r squared minus x squared. We're going to see this a lot. This is going to be a semicircle with radius of r. So in our case, what that means is our radius is 2, because we had a 4 here. So 1, 2, and 1, 2. I'm going to sketch in, hopefully something resembling a semicircle. And now I want to integrate between -2 to 2, which if I look, so this curve, between our curve and the x-axis, that area is the whole semicircle. So now I know that the integral from -2 to 2 of my function 4 minus x squared dx is going to be equal to pi. My radius is 2, and it's a semicircle, so I'm going to divide it by 2. So I get 2 pi. Okay, another example here. I have the integral from -4 to 1 of 3 dx. So what's happening here is that my function is equal to 3. So we can think of that as y equals 3. That's a nice easy function to work with because that's just 1, 2, 3. It's my horizontal line. Now I want to integrate my lower bound. My starting point is x equals -4. And I'm going up till -1. So my area looks like this, from -4, and I'm stopping at -1. So what I really want here is the area of this rectangle. So now my integral from -4 to 1 of 3 dx is just going to be equal to the base of my rectangle, which is 3, times the height. I guess I actually ended up making a square, and that gives me an area of 9. So again, big idea being we're just using geometry formulas to evaluate these areas right now. And so we'll do number 3 and 4 together when we're back in class. So for now, let's go ahead and move on. All right. So everything we've done so far has been just working with how do we calculate the value of an integral. And so right now for us, we said we calculate that value by using geometry. But now we really need to focus on the interpretation. So what do the answers actually mean? So in general, when we compute the value of an integral, of a rate of change function, we say that we are computing the change in the quantity being measured. So when we calculate the value of an integral, we're actually computing the change in what was being measured. So in general, we say if we're integrating the rate of change, right, that's going to be some kind of derivative that we're integrating. If we're integrating the rate of change of some stuff, the answer is going to represent just the change in that same stuff. So integrating the rate of change gives me the actual change, the amount of change. So let's take a look. An example here says if I'm integrating the rate of change of temperature, the number that I get out is actually going to tell me the change in the temperature. So integrating the rate of change of the temperature gives me the change. Now we have to be careful here when we're integrating the velocity of an object. What we have to remember here is that the velocity is the derivative of position. So velocity really gives me the rate of change of position. So when I integrate the velocity, I'm going to get the change in position. And if you think back, we had a vocab word for this, right? That was displacement. The change in position is our displacement. So we'll look at a couple of examples on how we interpret, and then that'll do it for today. All right, so let's see here. The following graph shows the velocity in meters per second of a particle traveling along the x-axis from t equals 0 to t equals 12 seconds. Okay, so along my x-axis I have time, and then my y-axis is velocity. So the first thing they're asking me to do is just find the value of that integral. So I know again that that's just the area between 0 to 12. Now there's a couple ways I could do this. So some people think of it like this. So I'm going to say kind of method 1. I could break it up into this triangle and then this rectangle and then this triangle as well. That would cover all my positive areas. So I'd kind of have 3 different regions, and then I have between 10 and 12, I have my negative region, which is a triangle. So let's say if I did it this way, I would have 1/2, the base is 2, and the height, it looks like, is 20. Plus, I have my rectangle, 1, 2, 3, it looks like the base is 4. The height is 20. And then I have my other rectangle, 2, 3, base of that one is 4, so 1/2 times 4 times 20. There's all my positive areas, and then I'm going to subtract off my negative area, which is 1/2 times base is 2, and the height of that is 10. So if I simplify, let's see, I get 20 plus 80 plus 40, and then I'm subtracting off 10. So combining those, I get 140 minus 10, that's going to be 130. Now, we have to think carefully about units. When we did our calculations, we were multiplying the base times the height. So we were multiplying, if we could think about it, seconds times meters per second. When I do that, my seconds canceled, so my units are meters. Now, another way, again, we're just still finding the value of that integral. Another way I could do it, because I like to make these as simple as possible, I know that this whole shape is a trapezoid, and I'm going to make myself a note. The area of a trapezoid is h over 2 times b1 plus b2. So the height of my trapezoid is going to be 20. So I have 20 over 2. My base along the bottom here is 10. My base up here is 1, 2, 3, 4. So now what took me 3 pieces before I can do in 1 piece. I still need to subtract off my rectangle here. So 1/2 times 2 times 10. But what we find out is either way, my positive area here is, let's see, this is 14 times 10 is 140. Then minus 10, and I still get 130 meters. So we can divide it up in a couple different ways, but we'll always get the same answer. So far we found the actual value. We did the calculation. Now we need to interpret the meaning in the context of the question. So here's where we need to think, right? I was integrating, we said velocity is the rate of change of position. So that means our integral is going to give us the change in position, right? So we would say that the integral from 0 to 12 v of t dt, it represents the change in position in meters, we're including units, from t equals 0 to t equals 12, and our time was in seconds. So that's what the integral represents. It represents the change in position over that time interval. So in our case, since that value was 130, since it's positive, I know that particle moved to the right. So I would say the particle moved 130 meters to the right from t equals 0 to t equals 12 seconds. Okay, so what that's telling us, right, is I know by looking at velocity is it was moving forward here because velocity was positive, and then it moved backwards. So really what happened is it moved 140 meters to, it moved 140 meters to the right, then it moved 10 meters back to the left. So in all, it ended up 130 meters to the right. All right. One last example. So now they're telling us that the function t of x gives the rate of change of the temperature of a cup of coffee measured in degrees Celsius per minute, and x is measured in minutes after it's poured. So now using correct units, interpret the meaning of this integral and the context of the problem. Now again, if I'm integrating the rate of change of the temperature, that's going to give me the change in the temperature. So 0 to 12, the integral from 0 to 12 of t of x dx represents the change in temperature in degrees Celsius, and then I'm going to state the interval from t equals 0 to t equals 12, and this one was minutes. Okay, I know that was a long video and it's a lot of information, but I wanted to make sure you had the basics for where we're going with integrals. We can address any questions that you've got when we're back in class, and then we'll give you a lot of practice with calculating and interpreting these integrals. All right, I will see you back in class.